Okay, in a series of IIR filter design example, we will discuss another example. So the provided question is, determine the order, cutoff frequency and poles of the Butterworth filter and sketch the poles of HAS with HA-S and also determine the digital filter equation HZ. And the given parameters are: passband attenuation should be less than equal to 1 dB, stopband attenuation should be equal to or greater than 30 dB, passband H frequency is equal to 200 radians per sample, stopband H frequency is 600 radian per sample. So now we will start our solution first by finding the order of the filter. In the first step, we will determine the order of the filter. For that, we will find out the value of passband ripple factor and stopband attenuation. So we know the relation AP is equal to minus 10 log base 10 1 over 1 plus E square, and AS is equal to minus 10 log base 10 1 by A square. So solving this, we will get passband ripple E equals to 10 to the power AP by 10 minus 1, which is equal to 10 to the power 1 by 10 minus 1 and gives the value of 0.5088. Now similarly, finding the value of A will be equal to 10 to the power AS by 10, which is equal to 10 to the power 30 by 20, and which will give the value 31.622. Now finding the order, N will be equal to 1 by 2 log base 10 E square over A square minus 1 upon log base 10 omega P over omega S. We have already know these relations from our lectures which we have already discussed. So substituting the values will give 1 by 2 log base 10 0.2588 over 998.95 over log base 10 0.333. Solving this relation will give N equals to 3.758. So the order of the filter should be integer. That means we will round off this N to the nearest integer. So N will now equal to, so first step we have find out the value of the order. In step 2, we will determine the cutoff frequency. We know from our previous lecture, omega C value will either depend upon the passband frequency or the stopband frequency, depending upon which should be matched perfectly. But in this case, it is not mentioned, so we will use omega P. So to exactly satisfy passband H frequency, omega C to the power 2n will be equal to omega P to the power 2n over E square. Then omega C will be equal to omega P over 1 by n. So it can be written as 200 over 0.5088 to the power 1 by n. We know the value of n is equal to 4. So we will get 200 over 0.5088 1 by 4. So this will give 200 over 0.844572, which is equal to 236.806 radians per second. So now we have obtained the cutoff frequency of the analog Butterworth filter. In step 3, we will determine the poles and sketch of the poles. Now we know N equals to 4 is the even quantity. That means Pk will be equal to omega C exponential j pi k n plus pi by 2n, for k equals to 0, 1, 2 up to 2n minus 1. Now putting the value of n, we get Pk equals to omega C exponential j pi by 4 k plus pi by 8, for k is equal to 0, 1, 2 up to 7. Now we will substitute the values of k and find out the values of pole. So first P0. P0 will be equal to omega c exponential j pi by 8 can be written as omega c. If we will solve this exponential j pi by 8, we will give 0.924 plus j 0.383. Then P1 will be equal to omega c exponential j pi by 8 plus pi by 4. Now solving this will give omega c exponential j 3 pi by 8, which is equal to omega c 0.383 plus j 0.924. After P1, we will find out the value of P2. P2 will be equal to omega c exponential j pi by 8 plus 2 pi by 4 will be equal to omega c exponential j 5 pi by, which is equal to, if we solve, omega c minus 0.383 plus j 0.92. Now after P2, we will find out P3. P3 will be equal to omega c exponential j pi by 8 plus 3 pi by 4 will be equal to omega c exponential j 7 pi by 8. If we solve this, it will give omega c minus 0.924 plus j 0.383. Then we will find out the value of P4. P4 will be equal to omega c exponential j pi by 8 plus 4 pi by 4 will be equal to omega c exponential j 9 pi by 8. If we solve this exponential term, it will give omega c minus 0.924 minus of j 0.383. If we compare P3 and P4, we find out P4 is nothing but a conjugate of. So now we are obtaining some kind of relation between the poles. So to verify, we will find out the value of P5. P5 is omega c exponential j pi by 8 plus 5 pi by 4, which will give omega c exponential j 11 pi by. When we will solve this, it will give omega c minus 0.383 minus of j 0.924. Now if we see this pole 5 and if we go and compare with pole 2, P2, that is this one, is omega c minus 0.383 plus 0.924, whereas this is minus j 0.924. So we can directly see P5 is nothing but a complex conjugate of P2. Similarly, if we will find out P6, it will be complex conjugate of P1, and if you will find out P7, it will be complex conjugate of P0. You can try yourself and see if these relations hold. Now we will sketch these poles in j omega axis and sigma plane. So P0 is 0.924 at the real point. So let's say it is 0.924, and the positive of j 0.383. So let's say it is located at some point here. Its complex conjugate, which is P0. Its complex conjugate is in the negative side of the imaginary axis, but with the same magnitude. So it is with 0.924 positive. Here lies the P7, this complex conjugate of P0. Now P0 onwards, P1 is 0.383, which will lie somewhere here, but its imaginary component is 0.924. So it will lie somewhere here. So it will be like this. So it is P1, and at the opposite end of this, here we will get the value of P6. Now if we move towards P2, we know the value of P2 is, in the real part, is minus 0.383. So it will lie again here, and its imaginary axis part is 0.924, which will again lie at this point. So this value is P2. Its complex conjugate is P5, which will lie at this point. Then for P3, the real part is minus of 0.924, which will lie somewhere here, and the imaginary part is positive with 0.383. So it will lie somewhere here. So it is P5 P3 and at the opposite end we will get P4. So now we have located all the poles in a circular manner like this. So all these poles will lie in a circular fashion, and in this plane the poles lying in this side are for HAS and poles lying at the right hand plane is for HA minus S. So now we can find out the value of HAS, which will be equal to omega c to the power n over left hand plane poles S minus Pk. So it will be omega c to the power 4 over S minus P2, as P2, P3, P4 and P5 lies in the left hand plane. So we will address only those planes. So S minus P2, S minus P3, S minus P4 and S minus P5. Now from the relation between P2 with P5 and P3 with P4, we can further solve this equation as omega c to the power 4 over S minus P2 with S minus P2 conjugate, S minus P3 and S minus P3 conjugate. Now we know omega c is 236.806 radian per sample and P2 is omega c exponential j 5 pi by 8. So P2 conjugate will be omega c exponential j 5 pi by 8. P3 is omega c exponential j 7 pi by 8 and P3 conjugate will be omega c exponential minus j 7 pi by 8. Now we can substitute these values and further solve this HAS, but right now we are not doing that particular thing. So we will directly move towards the step 4, that is to determine the digital filter response. Now it is not mentioned which transformation which we should use, so we will apply bilinear transformation. We will apply bilinear transformation, and in this case S will be equal to 2 by t z minus 1 over z plus 1, and taking t is equal to 1 second for simplicity, S will be equal to 2 z minus 1 over z plus 1. Then we can find out Hz will be equal to Hs, for S is equal to 2 z minus 1 over z plus 1. We know Hs is omega c to the power 4 S minus P2, S minus P2 conjugate, S minus P3, S minus P3 conjugate, which can written as omega c to the power 4 S square minus P2 S minus P2 conjugate S plus P2 multiplied with P2 conjugate. Similarly, S square minus P3S minus P3 conjugate S plus P3 into P3 conjugate. Now we want to see this particular part. Let's say if P2 is x plus jy, then P2 conjugate will be x minus jy. So P2 multiplied with P2 conjugate will be equal to x square plus y square, which is nothing but P2 mod of P2 square. So if we will substitute this term, then we can directly write this as omega c to the power 4 S square minus S P2 plus P2 conjugate plus mod of P2 square, then S square minus S P3 plus P3 conjugate plus P3 mod square. And for all these cases, S is equal to 2 Z minus 1 over Z plus. Similarly, in this side also, S is equal to Z minus 1 over Z plus 1 multiplied with 2. Now we can write this equation again as omega c to the power 4 S square minus. Please note that this P2 plus P2 conjugate, if you will add this P2 and P2 conjugate, it will be twice of x. So that means it is minus sign 2 times S real part of P2 plus P2 mod square S square minus 2s real part of P3 plus mod of P3 square, for s is equal to 2z minus 1 over z plus 1. Now if we substitute the value of s, it will be omega c to the power 4, and then this will be hz. It will be 4 z minus 1 z plus 1 square minus 4 z minus 1 over z plus 1 into real part of P2 plus mod of P2 square. Similarly, it will be 4 z minus 1 z plus 1 square minus 4 z minus 1 z plus 1 real part of P3 plus mod of P3 square. Now we can evaluate omega c to the power 4, which will come out to be 3144639,084.81. Real part of P2 will be equal to minus of omega c 0.383. Real part of P3 is minus of omega c 0.92. These values we have already evaluated in step 3rd. Then mod of P2 square will be equal to mod of P3 square will be equal to 1. These both values will come out to be 1. Then we can evaluate this expression substituting all these values in this equation, and solving this equation in the normalized form will give the value of hz, which we have already find out. So that's all for this lecture. Thank you.